So the midterm's on Thursday, and it's here in class. It'll be 80 minutes. And we also have an alternative time for those of you who are burdened by too many midterms, in particular if you have a lot on Thursday. So as I announced on Piazza, and some of you have responded that there will be a midterm option for Friday morning at 9 a.m., and it'll be in B205. But you have to let me know beforehand. In fact, let me know by today if you want to do this, if you need to do that option. Okay. We also had the Shazam competition, and Victor Ying won the competition, and yeah, let's give a round of applause. It was very fun, actually, because all of the 5 teams that competed did very well until we reached a certain noise level, and it was a lot of noise. And then they started breaking down, and they all suffered at about the same place. But the video of the competition is online with the lectures. It's very long and boring, but you can skip through it. You can hear how much noise they tolerated and so forth. Okay, so I'm going to go through. I know on the schedule it said we were going to do MRI and fun applications, and we're going to get to some of that at the end of this lecture. And those applications will be things that are not, you won't be tested on. They're just to bring this stuff to life. I like not to introduce too much new material on the exam week. But first of all, I want to just go over things we've learned and some new stuff, but basically bringing together the various things we've learned that I think will help you in preparing for the midterm. So first of all, let's do an example of a Fourier transform. And the reason I want to do this example, this particular example isn't that interesting, but I want to show you that there are often multiple approaches to doing these calculations. That's the fun thing about Fourier. We know so many cool properties. You can tackle the problem in many different ways. Some ways are much easier than others. In my example, there's not necessarily going to be any trick that makes it easier, but I just want to have gone through it in a couple of ways so you can see the different properties in action. Okay. So, for example, suppose you have x of t is the following. You have something like this. All right, 1 and 2. Okay, so if you have the following function and we want to take the Fourier transform. Well, of course, you can always plug this straight into the integral. And in fact, that may be the easiest thing in this case, but that's not how I'm going to do it because I want to go show some other options. Okay, so you could use the linearity property. That's often very useful to say, well, this is equivalent to the following sum of signals. I could do I'm going to draw it over here. 2 signals added together. How about one of them goes from -2 to 1 and one from -1 to 2? And these are just rects, but that have been shifted and scaled in time. Okay, and if you add these 2 together, of course, you're going to get the one up there, right? So by linearity, we can take the Fourier transform of each of these. Let's go ahead and do that. So I would write this first one here is, so x of t, let me go like this, x of t equals rect of t plus half over 3 plus rect t minus half over 3. Now, How did I get that? Well, I divide by doing divided by 3, I make the rect have width 3, right? And which both of these rects have. And then I do a shift. I replace t with t plus half. That's going to shift to the left by half. And the center of this is a minus a half. So that's good, right? Okay. So then here I can do the Fourier transform of each of these separately. And I can use our Fourier transform properties. We know that the rect goes to sinc of f. So I'm first going to peel off with the manipulations I've done here one at a time. So this is all right. So what I have is rect goes to sinc, rect of t. Therefore, rect of t over 3 goes to 3 sinc of 3f. That's the time scaling property. And therefore, what I have here, rect of t plus half over 3. Now, the difference between this and the previous line is now a time shift. Okay. Notice it's important which order I do this. I'd get the wrong answer if I do it in the wrong order. So here I have a time shift by 1/2. So the rule for time shifts is that I multiply in the frequency domain. So I should get e to the e to the I 2 pi 1/2 f is what I multiply by, and then by whatever I had before, which was sinc 3f. Is this making sense? That this is the, yeah, does this step make sense? So I just use the time shift property. Of course, those halves cancel. So then that means that this, so I can finish now and say x of f by linearity is 3 sinc 3f. I'm going to factor out the exponentials. E to the I pi f, and then plus, and the other one, the shift property would go the other way, e to the minus I pi f. Okay. And if I want, I can use Euler's formula here and say, oh, that looks like a cosine. Yes? So good question. If I could do this in another way. First of all, let me make sure I did it right, so I answer your question right. Yeah, I think I did it right. So I could write this. So actually, well, I'll do that next. This is the way I did it because I time shifted after I scaled. Once I've scaled, it's a new function. I'm writing it as rect of t over 3, but it's just a new function. And that new function was shifted by 1/2 because I replaced t with t plus 1/2. Okay, but I can do it your way as well, and we'll do that in just a moment. All right, so so I could write this as 6 sinc 3f cosine of pi f. Okay, so there we got it. Now you were saying this equals rect of t over 3 plus a 1/6, right? And plus rect t over 3 minus a 1/6. Okay, certainly that's equal. And this implies that we shift by a 1/6 and then we scale. Okay, why does it imply that? Because the sequence of functional manipulations would be start with what we have, rect of t, and the first thing that implies is replace this with rect of t plus a 1/6. That's a time shift by a 1/6. And now take this new function and do a time scaling. To do a time scaling, you just replace every t with t over 3, right? So 1/6. Okay, so these are two different manipulation orders. They get you to the same function we want. So this would be shift by 1/6 and then scale. Whereas the way that I did it was scale by 3, both times you're scaling by 3, then shift by 1/2. Now, of course, if we did the Fourier transform rules to this new path, it should get at the same answer. So this would imply that goes to, of course, sinc of f. This goes to e to the I 2 pi 1/6 f, sinc of f. And then this one here, I replace every, now the time shift property, the time scaling property should be 3, but then I replace the above, I have to shrink in frequency. Okay, to shrink in frequency, I replace every f with 3f. All right, so e to the I 2 pi 1/6 3f, sinc 3f. And we see we get at the same answer once we multiply the 3 and the 6th. Okay, so both paths got us to the same answer. All right, that wasn't the other way I was going to do an example of. We could have done this decomposition. We could have said, well, that's the same as these two things added together. All right? So this is, in other words, we could have said x of t equals rect of t over 2 plus rect of t over 4. All right? And then use the Fourier transform properties on that. That should be very simple. So we'll go down here. We'll say, I'll repeat what I just wrote, equals rect t over 2 plus rect t over 4. Therefore, x of f equals, and now we just need to do the scaling property. So equals 2 sinc of 2f plus 4 sinc of 4f. And that was actually very simple. Now you might say, wait, this is one answer is this, and the other method gave us something completely different. And if you use the trig identity, you'll show these are actually the same. Either one of these would be an acceptable answer, and they're actually the same thing, but they just don't look the same. But sinc is sine over, is a sine over the argument, and so you have a sine times a cosine over here, and you could use a trig identity to split that into a sum of two sines. Okay, let's do another example. Again, the purpose of this example is really just to show you another way to do it. I mean, it's not necessarily true that these manipulations in my specific examples make the problem easier. Okay, maybe just integrating is easier. So let's say that x of t equals the following. All right, so I've come up with some crazy signal that looks like this. It goes like the following. All right, that's our signal, 0 over here. And we want to know the Fourier transform. So here the method I'm going to use is I'm going to split this. I'm going to use the multiplication rule, the modulation rule. Okay, I'm going to say, let's first look at something that we'll define. We'll just give it a name, y of t. And this is going to be this part over here. y of t is going to be something very simple. U of t e to the minus 2t. Okay, I'm starting with this because this actually is a signal that's very important and common, one that you'll get familiar with, and it's also something you would find in a Fourier transform table. So in practice, I mean, this would be something you would not have a hard time taking a Fourier transform of. We will do it by integral here. So this simple signal, this is simply a decaying exponential times 0, right? And the Fourier transform of this thing is going to be y of f is the integral notice I've taken the u of t into the limits of the integral. That's why it doesn't appear here. And of course that's just an integral of, we can combine the exponential term here. And that equals one over it equals that. Okay, so here is the Fourier transform of this decaying exponential that starts at time 0. In fact, it's useful just to look at this thing. Roughly, what does it look like in the frequency domain? This is a little bit of an aside from my example, but while we're here, let's in frequency, this thing, the magnitude of yf is symmetric in frequency. Its peak is at frequency 0. Frequency 0, it is 1/2. Right, we can plug in f equals 0. And it falls off as the frequency gets positive or negative, symmetrically. And notice that we did a specific case where the exponent was -2, but in general we could have said minus a. And what we would get here is that a would just show up right here. And effectively that would affect the width of this thing. So this doesn't have a sharp cutoff, but approximately the width is related to the point at which the frequency term here becomes larger than the real part here. The frequency is an imaginary part of this denominator. So when this part of the denominator gets roughly bigger than the real part, you start to get a significant fall off. Okay, and then you fall off like 1 over f. Oops. So this width will be something related to, let's say, like a 2 over 2 pi, right? So it'll be like a 1 over pi width and frequency, something like that. All right, I won't draw the phase. Of course, it has a non-zero phase too. But I won't attempt to draw it here. Okay, so now what do? We say, all right, what I want to do is I want to split this into 2 parts. I want it to be this part and this part. And then I'll use the multiplication rule. So notice that y of t minus pi, all right, is going to equal u of t minus pi e to the minus 2 t minus pi. I'm going to factor that thing out. So I have an e to the 2 pi here. So what I can do is put an e to the negative 2 pi on both sides, and that's going to have the effect of getting rid of this thing. Okay, so there I have an equality, and now I can use my Fourier transform rules to say that, therefore, the Fourier transform of this thing equals, this is just a constant, e to the negative 2 pi. By linearity, it comes out. And now I want to do e to the negative I 2 pi, and then the time shift was by pi f, right? And then y of f, which we have above, right? Okay, so that equals all right. Now the final thing is to go look at the Fourier transform of this other part, the sine. And let me ask you, what is the Fourier transform of sine of t? So we can only do this because we've allowed ourselves the delta function. Okay. Now, we'll talk about this a little more today. The Fourier transform is not well defined for periodic signals. But because we've allowed ourselves to use the delta function, we'll use it here. And we'll say that we can define a Fourier transform for this. It's going to be a sum of two deltas. Okay, so this thing, so sine of t goes to 1 over 2i delta of t, delta of f plus 1 over 2 pi plus 1 over 2i and we'll talk more about doing this later if it's confusing to you. You can always plug this into the inverse Fourier transform to check. So really, if you want to take a Fourier transform of a periodic signal, the only real way to do that is by inspection. In other words, by realizing that if I use Euler's formula to separate this into two complex exponentials, you just have to memorize that pair. A complex exponential goes to a particular delta function. You can check it in reverse, but you can't derive it forward, okay, using the integral. I think I've mentioned that before. Okay, so what we have then is that the result, x of f, should be the convolution of these two things. So it's this thing convolved with what we have up above, which is 1 over 2i Okay, and convolution with delta functions is very simple. All right, so convolution with a delta function is simply shifting the other signal to the location of the delta function. All right, so in fact, what we are going to have is this. First of all, let me just intuitively, let's get a sense of what this is going to look like, since I'm not going to plot it, but we'll write it out. This function here is not very different than this one that we originally wrote up for y, for the magnitude of y. Okay, it's not very different. The difference is it's this y of f with a linear phase shift and a scaling. Okay, so in terms of magnitude, it's no different than y of f. The phase has changed. All right. Then what do we do with this convolution? We take this this new thing here, And we add it together at two different locations. Well, we have a scaling, another scaling of 1 over 2i. Not very interesting. And then the convolution with this delta function shifts it over to center it at 1 over 2 pi. And convolution with this delta function shifts it over this way to center it at negative 1 over 2 pi. And then they'll be added together. Okay, so that's what the result will be. So we can write that down and say that equals, there's just going to be a lot of writing here. It's going to be e to the negative 2 pi over 2i. Let's factor all that out. And it's going to be e to the minus I 2 pi squared f minus 1 over 2 pi. Whoops. So I'll multiply that out there. 2 plus 2 pi, right? F minus 1 over 2 pi. Oh. Yeah. Okay, so it's going to be 2 minus I plus I 2 pi f. Did I do that right? Yeah. Looks right. All right. Plus, and then the other term here, just shift the other way. All right, and there's the result. Voila. Okay. Any questions about this? I know it's a lot of busy work. Hopefully you've seen a few of the properties in action. We've used most of our Fourier transform properties to do these examples. Okay. Let me go back and emphasize how you can do this Fourier series or Fourier transform by inspection, I keep saying. In your problem set, you had the following. From PS1, from the first problem set, you had this. You had an x of t, which was e to the minus I pi t, plus e to the 2, 1 plus I pi t. Okay? And you were asked to do a Fourier series, calculate the period and the Fourier series coefficients, right? The first thing to do here is to say, well, let me look at the periods of both of these parts here. I need to figure out the period. And this part here has period 2, and this part here has period 1. I know that because, first of all, this is written in a complicated way, but it can be rewritten as, well, you know, the e to the 2, I can factor out the top part. I have e to the 2 times e to the I 2 pi t, right? So I'm really just looking at, this is a complex exponential, has a frequency of 1/2, therefore a period of 2. Okay, is this a question? No. Okay. And then here I have e to the I 2 pi t. That's got a frequency of 1, so a period of 1. And sinusoids, if you add them together, you're going to get the overall period of this is the least common multiple, so it's 2. All right? So period 2. All right? So then now, what many of you probably did is then plug this into the Fourier series integral to get the answers, all right? But you didn't have to do that because you could do the following. You could say, let me write this now in a way that looks like a Fourier series synthesis equation. Remember, analysis equation gets you the coefficients directly. But the synthesis equation puts x back together, right? And a synthesis equation is the sum of complex exponentials, so I'm going to write it that way. E to the I 2 pi minus 1/2 t plus e squared e to the, let me put a 1 here just to be even more clear. E to the I 2 pi 2 over 2 Okay, so this is the same equation. Now, why am I putting these 2 over 2 there and things like that? Why did I do that? Well, remember, the equation looks like this. It's the sum over k of ak e to the I 2 pi k over t. And what did we say t was, right? We said t equals 2. Period is 2. So I just wrote my x to look like that sum. All right. So now I can read out the coefficients exactly, right? This becomes, that is a of -1, and that is a2, and all the other coefficients are 0. And that was the answer. Even if you did the integral, you're going to get that answer. Right? Okay, so sometimes you're lucky, and in inspection, if you have a complex exponential in your signal, then just converting that directly to what you know it's going to be. You know that's going to contribute one term of the Fourier series. That can be the fastest way to do it. You can use linearity. So if it was like a complex exponential plus something else, just pull out the complex exponential, handle that yourself, and do the integral on the rest or whatever. So the same thing applies to the Fourier transform, because in that case, in the Fourier transform case, you can't even do this signal with the integral. It doesn't even work. What is the Fourier transform of this, of x of t? Let's see. Continuous time Fourier transform. What is x of f? Anyone? Something with delta functions? Yep, delta of f plus a half. Okay. So it actually will be plus a half, plus e to the e squared delta of f minus 1. Okay? Now, if you don't trust me, you go plug this into the inverse Fourier transform equation. It's easy to take integrals with delta functions. You're going to get back this signal here. So that's how you can check this. We will give a formula very soon for just converting these, okay? And it's a simple process. You see that the coefficients, I took the AKs and I multiplied each one by a delta function. All right? And I shifted that delta function to the frequency. So if you remember, we had, well, I guess the main point I want to make here are 2 points. That delta functions allow us to use the Fourier transform. Instead of just the series. So we had this series which was built for periodic signals. Well, now we're saying, yeah, the Fourier transform itself can handle them as long as we use delta functions. And 2 is that this must be done by inspection. So you have to match up. You have to decompose it yourself. Must be. In other words, you have to take your signal, separate out the sinusoids into complex exponentials, and just use the Fourier transform pairs that you know to do it. Okay. So that brings us to a nice discussion on unifying the different Fourier transforms and series that we have. I'm going to draw this grid, which is which is a useful visualization. We have four things we've been introduced to. We have let's say the continuous time Fourier series, the discrete time Fourier series, continuous time Fourier transform, and discrete time Fourier transform. We have certain things, formulas and things we remember for each of these. For example, the Fourier series, you assume you have a period t. For the discrete time Fourier series, we'll use n just to imply that it's discrete time, that it's an integer period. Right? Okay. And we have a formula. I'll write in these formulas here. AK equals 1 over t, integral from 0 to t of x of t, e to the negative I, 2 pi, k over t, t. And a reconstruction, which is that x of t equals a sum over all the k's, ak, 2 pi, k over t, t. Okay? The discrete time one is very similar. There's only the difference only being that it's a sum here, right? Well, there's one more difference. N equals 0 to n minus 1. The difference is in the synthesis part. What's the difference here? Does anyone remember? You only sum n of the reconstruction components. Okay, so you don't sum over all k. Let's say k equals 0 to n minus 1. Any period of n of them will do. You could do some negative, some positive, as long as you're covering one full period. You'll get the same answer. AK. Okay, so I'll highlight that. Okay. You don't sum all over all k. Now, why is that? What is fundamentally the difference between discrete time and continuous time? We have aliasing, exactly. So aliasing means that exponential functions, complex exponentials, sinusoids, that on paper look different, the formula is different, are actually exactly the same in discrete time if their frequencies differ by an integer value. Okay. So what that means is if we calculate AK and we also calculate AK plus cap n, we will always get the same value because, in fact, this exponential function here is the same for both for values of for coefficients that differ by n. Right? If we plug in k plus n instead of k, then we factor out the n over n. We get an integer. The difference between the frequencies is an integer. They're exactly the same. Therefore, the coefficients have to be the same. And so this aliasing also is part of the reason why we only sum over one period. Because this aliasing means that the AKs will in fact be periodic themselves. All right. If you summed over all of them, you would get nonsense. You'd get infinite values. Okay. So how about this? Here we have XF equals the integral and we get back to x of t by almost the same thing. Whoops, no negative. It's the only difference. Okay. And the discrete time Fourier transform is basically the same, except again, in the inverse part. Okay, the inverse part here is that xn is the integral over just one period. Now, is this going to be periodic? What will be the period of xf? Again, because of aliasing, and this is one of the key features of the discrete time Fourier transform. One thing that makes you know you're dealing with discrete time, because due to aliasing, x of f will be periodic with period what? 1. And you get that because you said, oh, if f differed by 1, this is the same exact discrete time signal. Okay, so we just integrate over one period. We can do it 0 to 1. It's more traditional to do negative a half to a half, not that it matters. So integrate from negative half to half, xf e to the I 2 pi f n df. Okay, so these are our 4 Fourier transforms, so to speak. Let me highlight this. Now, what we can do is we can list out some of their distinguishing properties. The Fourier series is this top row, right? So in the time domain, these are periodic. In time. All right? And in fact, the Fourier series is designed to work on signals with finite power. It's only intended to work on signals with finite power. So now if it's discrete time, it's always going to be finite power if it's discrete time and periodic. If it's continuous time, you can create a periodic function that has vertical asymptotes and is not have finite power. Okay, and then it wouldn't work well for the Fourier series. But so the Fourier series is intended for finite power for periodic signals. Now these are not periodic, and so the Fourier transform is intended for finite energy. Okay, so a finite energy signal would be one that eventually dies off, doesn't have more content in time. Okay, maybe it doesn't have a sharp stopping time, but it trickles off. So, but we've seen, of course, we've seen that the Fourier transform can in fact handle the periodic ones as well, and that's because we cheat the math and we use a delta function, right? Okay, now how about the columns here? This is continuous time. And discrete time. Now let's see what we know about these in the frequency domain. I'm going to use a different color to highlight the properties of the rows and columns in the frequency domain. Okay, so in the frequency domain, continuous time, let's start with the left column. Continuous time, this is aperiodic. Here, this was aperiodic. And so black means time domain, and here I'll put a little key here. Frequency domain, time domain. Oh, I should have used different colors. I have blue and black in the table. I'm going to do this. I'll highlight. Okay, so we've got in the time domain, we have these properties. And And we have these important properties in the frequency domain that the discrete time Fourier series and the discrete time Fourier transform both become periodic in the frequency domain due to aliasing, right? And what about over here for the Fourier series? We always have discrete frequencies. We have a sequence of coefficients, not a continuum, right? So these become discrete in frequency, and this is continuous. So we have this, our table illustrates duality here because we see that the columns for the meaning of the rows in the time domain is the same as the meaning of the columns in the frequency domain, and vice versa. Okay, so it's very important to remember that discrete time transforms are periodic. In fact, if you see a periodic Fourier transform, your brain should trigger that this is a discrete time process. All right. So I'm going to further try to unify this, but I should not go on without mentioning that we did learn about another transform, the DFT. Remember, that's what the FFT is computing in MATLAB. Right. The DFT, I'll put another box here. DFT, as I described before, it approximately equals the DTFS. Okay. So the DFT is intended for finite duration signals, discrete signals, right? So it's finite duration discrete time signals, a vector. All right? But if you look at what the Fourier series does in discrete time, it only calculates on a finite duration of x on one period. So even though we said the Fourier series is intended for periodic signals, it very well could be used on a finite duration signal. And the interpretation, if you use the Fourier series on a finite duration signal, the interpretation is that you're imagining that all the stuff beyond the vector you have is just the periodic extension of what you have. Okay. So technically, this is written as the Fourier series is, sorry, the DFT is this. And the inverse is where the 1 over n comes in. Oh, no one corrected me that I put a t here. It should be an n. Okay. So in formula, it looks exactly like this discrete time Fourier series. That's why I say it is basically the same thing. You just move the 1 over n. However, there's even another way to interpret this DFT, and maybe this will justify why the 1 over n moved. And that is that if you look at the discrete time Fourier transform instead of the Fourier series. So now suppose we tried to use the discrete time Fourier transform on our finite length vector. Okay? Here what we're going to do is we're going to pretend that everything outside of the vector that we have is actually 0, rather than the periodic extension. For the Fourier series, we had to imagine that it was the periodic extension. Here we're going to imagine that it's 0 everywhere outside that vector. And we're going to apply the Fourier transform to this. It's aperiodic, right? And when you plug in to this equation here, plug that in and evaluate only at certain frequencies. Okay, because this is meant to be evaluated at any f. Just evaluate at certain steps, k over n. You'll get exactly these AKs. Right? It's the same exact sum. So this probably motivates why you would put the 1 over n on the other side if you want to interpret the DFT as a sampling of the discrete time Fourier transform. It's a different interpretation. It's a sampling of the Fourier transform at particular frequencies, okay? And the interpretation is that you're treating your signal as if it's 0 everywhere else. Okay, so you have some finite duration signal, you put zeros everywhere, take the Fourier transform, but only keep certain samples, and that's the DFT. So 2 interpretations. The other one is, as we just talked about, that the DFT approximately equals the discrete time Fourier transform. Either way can be helpful in thinking about the DFT. In fact, I find the interpretation of it as being like the Fourier series. I find that as more helpful because when you want to know the properties of the DFT, there's some important properties of the Fourier series that come out. So let's just talk about what are the differences between these. And the first thing to notice is that they all can be understood as continuous time Fourier transforms under the right translation. Okay, so for me, I find it very helpful to just know the continuous time Fourier transform very well and know how to translate each of these over to it. All right. So here's what I mean by that. Represent discrete time as continuous time using delta functions. Let's see how we can do that. So suppose we have a discrete time signal x of n, and we do the following simple translation. We define something x of t that will equal the sum over n, let's say sum over all n, x of n delta, discrete, this is the Dirac delta function, t minus n. Okay. So this, I defined a continuous time signal, but I used the discrete time signal to define it. All I've done here is I've said, if I have some n here and I have some discrete time signal like this, say there's 0, 1, 2, then I've converted this to a continuous time signal that is just delta functions at each of those points. Okay, so the obvious thing to do, let's just take our discrete time signal and each point turn it into a delta function in continuous time. Now, how then would let's look at what the relationship is between the discrete time Fourier transform of xn. So the Fourier transform of xn in discrete time equals, we have a formula for it right up here. This is the discrete time Fourier transform. Let's do the Fourier transform of our new x of t. That's going to be the continuous time Fourier transform, right? Because it's a continuous time signal. And we'll plug in this. Okay, now let's change the order of the sum and the integral. And notice this integral is with respect to t. There's no t in xn. So it's like this. And now we use the shifting property, and that just becomes e to the minus I 2 pi fn. And that's the definition of the discrete time Fourier transform. I'll say that equals the Fourier transform of xn. So this translation of discrete time to continuous time keeps the Fourier transform exactly the same. So everything we knew about the Fourier transform in discrete time should carry over to continuous time if we think of discrete time signals as being delta functions in continuous time. Okay? Similarly, what if we interpret, in the frequency domain, suppose we have a period and Fourier series coefficients of a signal. Period t and a set of AKs that define a signal in the Fourier series, right? But we can define a function xf, which is just those AKs attached to delta functions. AK delta f minus 1 over t, actually minus k over t, and sum it for all k. So again, this is just taking our AKs and building them. We're building an XF out of our AKs by assigning them to different frequencies. So for frequency 1 over t, we put a delta function with A1. And we have A0 here. And 2 over t, we put A2, and so forth. Okay. This is like we talked about representing the Fourier series in the frequency domain. We already said the A's should be associated with particular frequencies, k over t. And all I'm saying is do this formally. Take your Fourier series coefficients, attach them to delta functions in the following way. And what we have now is, let's see if this makes any sense, if this XF makes any sense as a Fourier transform, okay, of our original signal. Well, if we take the inverse Fourier transform of this, then that would be an integral over one period of this thing here, sum over k, df. All right. So this is going to be, now again, switch the order and integrate 0 to 1 of this thing. And here, only if the delta function is in the interval do we count it. Now, really, I should integrate over one period. The problem is the edges of this interval, 0 to 1. Some delta functions are right on the edges, so I'm going to say 0 minus epsilon, 1 minus epsilon. Okay, that way the delta functions aren't right on the edges. And what I get is that this is 0 if the AKs are not in the first period. So I'm going to get zeros except for k equals 0 to n minus 1. And for the rest of them, the delta function is in that interval. And we get e to the I 2 pi, and we replace f with k over t, t. Okay, voila, this was back to x of n. So, in other words, x of n, the Fourier series coefficients of x of n, if they're interpreted as a Fourier transform with delta functions, then they also represent that same discrete time signal. Okay, so this is all meant to show you that now that we have these magical delta functions, all of these different Fourier transforms can all be interpreted as one, the continuous time Fourier transform. Which means that properties that you expect that work for continuous time Fourier transform are going to work for the others. But you have to be a little bit careful. Here's how you have to be careful. For example, we have a time shift property for the continuous time Fourier transform. But the time shift property will only even make sense in discrete time if it's a shift by an integer. Okay, so don't try to use the time shift property for discrete time if it's not a shift by an integer. It just doesn't make sense, right? the time scaling property that we learned in continuous time is a little bit problematic in discrete time, because how do you define a scaled signal? You have to be careful. There are ways to carry it over, and you did that in a problem set where you inserted zeros and so forth. Now, the biggest one you should remember that you don't want to apply directly, that we learned from the continuous time Fourier transform, that doesn't directly apply to any of the others, is, well, we have a convolution property that says convolution in time is multiplication in frequency, right? That's a very important property, but you only want to apply it directly to this bottom row, and here's why. Remember that this top row, these were Fourier series. When you interpret those as a Fourier transform, they have delta functions, right? And we don't have a good way of interpreting multiplying delta functions. Okay, so in fact, the convolution property that says multiply in the frequency domain should not be used for these Fourier series. There is another property which we'll talk about in a couple weeks. It's called circular convolution. When you multiply in frequency, you're doing something else called circular convolution if you're in this Fourier series space. Okay, so don't worry about that now. Just realize that the convolution rule, it only works for the Fourier transform because, again, the way to remember why this happens is just to think, how would I multiply delta functions in the frequency domain? That we don't have a way of making sense of that. Okay, and then, of course, the dual property that says multiplication in time is convolution in frequency. Again, that's only going to apply to which spaces on this table? These two transforms at the bottom? Not quite. Continuous time. So it's only going to apply to continuous time. Because in discrete time, again, we're interpreting discrete time as delta functions. Our signal in time is delta functions. We don't want to talk about multiplying two discrete time signals if we're talking about multiplying delta functions. It doesn't make sense. So that analogy from continuous time doesn't carry over to discrete time. Now, again, there will be a cool property of what happens when you multiply two discrete time signals. And by duality, it's going to be a circular convolution in the frequency domain. But just don't worry about that right now, and realize that it doesn't carry over directly, because multiplying discrete time signals under this delta function interpretation doesn't make sense. Okay, we might talk about duality, and duality is interesting because in continuous time Fourier transform we already stated what duality is. Forward and backwards are the same, basically. Notice, though, that duality doesn't really make sense here because one of them's a sum and one's an integral. These aren't anything like each other. Okay. The only other place duality really makes sense is all the way over here in the discrete time Fourier series, because there you do have basically the same operation forward and backwards except for the 1 over n. Okay, so they're both sums. So duality is funny. It sort of flips this table along this diagonal. Okay, the continuous time Fourier series is dual to the discrete time Fourier transform. How are they dual? Well, let's look at their properties. The continuous time Fourier series is discrete and so it's periodic in time and discrete in frequency, right? And the discrete time Fourier transform is discrete in time and periodic in frequency. Okay. Okay, I want to do an example, and you already have some of these, but this is an example of system, of checking some of the properties of a system. So I know you didn't have a lot of these in your problem set, and I figured these are good for study for the midterm, so you can go look at lecture notes that Cy gave in his lecture where he went through some examples of checking whether a system has certain properties. So I'll just do one example here. Like I said, go back and look at the notes if you have a hard time with this. Suppose you have a system that we casually define in this way. We say that y of t is the output of the system and the input is x of t. Then this is what happens to any x of t. This notation means that that any signal that you put in the system will come out delayed and multiplied by t squared. Okay, that's what it means. So we could check things like linearity, and that we check in the following way. We say, what if I put a x of t plus b y of t into this thing? What's going to come out? Let me apply that operation to this. So I should have t squared times the delay of my input. My input was ax of t plus by of t, so I get ax t delayed plus by of t delayed. All right. Okay. Now, and I can simply factor and say that that's a t squared x t minus 1 plus b t squared y of t minus 1. And this is simply the result of putting ax of t in, and this is the result of putting a by of t in. So linearity holds. Okay, so yes. All right, but you can check now time invariance. And here you have here you put in, okay, so now what we want to do here is say, what if I delay x of t? So I put x of t minus tau, some arbitrary tau. All right, what's going to come out? Well, this new signal, it's a function of t, it's a signal of t. The system always takes that signal and delays it by 1. So this is, and multiplies by t squared. So what comes out here is t squared x of t minus 1 minus tau. Right? And that does not equal t minus tau squared x of t minus tau minus 1, which is what we expect. It doesn't equal it in that first term. These are not equal. So not time invariant. Okay? We could check, is it causal? Well, let's say, is it memoryless? Memoryless means that the output at any given point in time only depends on the input at that point in time. This is no. Depends on the past, right? Is it causal? Now we just want to know, does it depend on the future? But we see from inspection very easily this only depends on the past, not the future. Okay, so yes. Is it stable? Stable, we've defined to say if the input is bounded for all time, can I give you is there some finite number I can give and guarantee the output will be less than that in absolute value? And this is no, and then by an example, let x of t equal 1. Therefore, the output y of t equals t squared, which is unbounded. The input was bounded, the output's not bounded. Right? Okay, and then finally, is this invertible? So if you, for any x, if you put an x in here and out comes y, can you always recover x? Yes, no? Should we vote? Well, you could try to do this. X of t minus 1 equals y of t over t squared, right? Therefore, x of t equals y of t plus 1 over t plus 1 squared. Okay. The only problem is when the denominator is 0. Okay, so I would say this is almost invertible. If you knew, for example, that x was continuous, then fine, it's invertible. If you don't know that, then it's not invertible because you'll lose one location of x. Right? So, Okay. All right, let me move on to something else. Okay. Suppose, let's look at something fun here. Suppose you you have an LTI system. LTI. It's a system called H, has an impulse response. And you put into this thing a complex exponential signal. Your signal is just e to the I, 2 pi, some constants. I'll use capital F to represent that constant frequency, times t. So it's a continuous time signal, goes into your LTI system. What comes out of this thing? Perfect. So what comes out here is the convolution. So convolution. You get that thing convolved with the impulse response. So let's say h of tau. And then this input here, e to the I 2 pi f. And then you have to have t minus tau. D tau. Right? So there's convolution. Well, this exponential can split into a product of two things. And the one with the t in it instead of the tau does not depend on tau. It can move out of the integral. So that equals e to the I 2 pi f t times an integral here. And what's that integral? We might recognize this. What is the Fourier transform? Evaluated where? So it's just a number. Fourier transform gives us a whole function. So where is it? Is the Fourier transform evaluated at what point? Yep, capital F. So it's h of capital F. That one frequency. So that's just a number, right? If you evaluate the Fourier transform at a particular point, you get a complex number. So this is cool because what it says is you get the same function out, but you multiply it by some number. Maybe there's some gain. Maybe it has a phase that becomes a time shift. In fact, this is, and we didn't even assume anything about our system except that it was LTI. So when our system's LTI, if you put a complex exponential in, you get the same frequency complex exponential out, just scaled. These are called eigenfunctions. And so, in fact, that motivates why the Fourier transform is so special, why it has the convolution property, because it's using the basis that are eigenfunctions for any LTI system. Okay. So then that means that if you want to, so if you put like a sine in, or cosine of 2 pi f t, then what you can do is use Euler's formula to split that into two exponentials, apply what we just did to each one. And I'm just going to save you the work here. You get the magnitude of h of f times cosine of 2 pi f t plus the phase. So you get the phase shift in here. This is the phase of h of f. That's what comes out. Okay. By the way, we could have done this another way. We did it directly using convolution, but we could have done this with the Fourier transform property, right? Because the Fourier transform of this thing is what? It's a delta function, delta of f minus capital F. That's what the Fourier transform of that is. Okay. So we have a rule that convolution between h and f should just be multiplication in frequency. We should have this delta function times h of f. So then over here we would have, let's take that over here. So then we would have h of f times delta of f minus cap f. And we already said that if you have a delta function times the continuous function, you can just replace that with h of cap f. This is the sifting property used without the integral. But And so that's what the Fourier transform should be of the output. Take the inverse, you get this. Okay. Let me say something else here. I want to show you something else cool in the last 2 minutes. Notice that you could I'm going to show you that sometimes inspecting these formulas at particular points of f are interesting. So first of all, if you look at the Fourier series and look at the formula for A0, okay, Fourier series, you had a periodic signal. A0 is, we have a general formula, AK equals something, but let's plug in 0 because it simplifies. We get a 1 over t, integral from 0 to t, x of t, and then we have an e to the 0, which we'll leave out, dt. And this is an average. So A0 actually has the 0th Fourier series coefficient has a significant meaning. It's the average of our signal. We tend to call this thing DC offset, direct current. So we call that the DC offset of a signal if you have a periodic signal that has a non-zero average. Remember in Shazam you subtracted that out. Okay. So the Fourier series, that corresponds to the Fourier series coefficient at 0. Equivalently, it's the DFT at frequency 0. Okay. Now, similarly, if you look at x, the Fourier transform evaluated at 0. Again, we can just take the formula that gives us x of f and plug in f equals 0. And we get that this is the integral of x of t e to the 0 dt. Okay. So sometimes, this interpretation is nice, that sometimes you might be interested in this quantity of a function. You might not be caring at all about the Fourier transform. You just want to know what's the integral of something. And if you know the Fourier transform, just plug in f equals 0. There's your answer. Right? Okay, so that's kind of a nice, there's sort of a, you could do this for any particular frequency and get all sorts of formulas, right? But the f equals 0 formula is useful. There's something else interesting if you did, here's something similar, but maybe you'll think this is a little weird. Take x of t convolved with x of negative t. So you take a signal, convolve it with itself flipped. There's a name for this. People call this the autocorrelation function. Okay. Don't worry about its significance, but evaluate that output at t equals 0. Okay. Now this looks weird because it looks like I'm just plugging t equals 0 to each of these places. That's not true. Remember, convolution is on the whole signal. Evaluate the result at t equals 0. But when you write out what this is, it's the integral negative infinity to infinity of x of tau, x of negative t minus tau, d tau. Okay, now if we evaluate this at a particular point, t equals 0, right? Then it's just, oh, let me add a conjugate. I always forget the conjugate because I think we're doing real signals. Let's do the conjugate of the second one. That's how autocorrelation is really defined. Okay. Then what we get is this equals integral x of tau, x conjugate of tau, d tau. And what is this? What was that? It's the energy. So that's another thing. We're not going to use the autocorrelation function. If you do more signal processing, you will. And anyway, it's kind of cool that if you have the autocorrelation function and you just look at one point, that tells you the energy of the signal, right? So I just want to bring these examples up as there are ways of using these Fourier transform formulas, evaluate at specific points, give you interesting formulas, right? And I'm going to make one more point. I'm sorry, we're a couple minutes over, but the notion of invertibility we talked about whether a signal is invertible. For LTI, invertibility is simple for LTI. Because an LTI system is defined by its impulse response. Right? So the entire system is defined by this impulse response, h of t. Of course, if you know the frequency response, h of f, well, that also tells you h of t, so that also defines the entire system. If you look at the frequency response, okay, of a system, by the convolution rule, we know that any input to a LTI system, in frequency, you just get a multiplication. Right? So if you think about how you would go about inverting an LTI system, and something we'll look at when we talk about filtering and so forth, the way you would invert an LTI system is you would want to undo that multiplication. Right? So you have your x of f that went in. It was multiplied by h of f. To undo it, you should divide by h of f. Okay? And then, of course, go back to the time domain with an inverse Fourier transform. So would this system here be invertible? If I've drawn, what I've drawn here is the magnitude of h of f. No. So what if I have an input signal that's like this? What if my input signal has like part here and part here? Well, I'm going to completely lose this part once it multiplies by 0. There's no way to get that back. Right? So if the Fourier transform, if the frequency response has 0 magnitude for a portion, then you'll never recover that part of the signal. Now again, as we saw before, I mean, points like this, yes, there's 0 magnitude, so technically you'll lose a frequency component there. If there was a delta function of your input signal, it would be completely lost. You would lose that. But for the most part, if it's continuous, if you knew it was continuous, then those points are fine. You'll still recover those isolated points. But if there's a region of 0, then you'll lose. You can't invert.